This is kind of a standard title for my talk, some combinations of machine learning and theorem proving, but I'll try to sort of speak a bit more about what I was kind of asked from the organizers, like about like AI for understanding mathematics, etc. So as you already heard, like almost some 30 years ago when I was studying math, I started to ask these questions like how do we automate it, right? And obviously at that point you learn about all these like undecidability and incompleteness results, etc. But like my feeling still was that what we are doing as humans might not be so unapproachable to machines. And there was this field of automated theorem proving, which is like a very old, like maybe one of the first fields of AI. Also, so by the way, that's an answer to one of the questions given to me by the organizers. Like, what about using AI for theorem proving? Well, the answer is that during the history of AI, theorem proving used to be AI. It was actually one of the first fields of AI. And there are like these pendulum swings, right? Like that suddenly something totally different is considered to be AI today, but maybe tomorrow theorem proving, maybe with some combinations with other algorithms will again be considered to be AI. So I see this as one kind of big landscape. And so already like when I was thinking about this like some 30 years ago, it became to me kind of indispensable that we have to include learning, like that what I'm doing as a student of math is somehow learning from my successes and failures, and this learning is kind of informing my further attempts and explorations, and that there are probably some pretty complicated or maybe not so complicated feedback loops about like the exploration, the deduction, and the learning that we should be exploring. So that, as you heard, that was kind of already my master thesis, in which I was using symbolic machine learning at that point called inductive logic programming, which may again be pretty interesting today, especially in combination with like the statistical machine learning methods, because it was kind of explosive at the time in the same way as, for example, theorem proving was explosive because the combinatorial search was big. But in a similar way as we are today sort of pruning the combinatorial search by the learned experience, in theorem proving, we could also be learning the search for algorithms like crisp algorithms using statistical machine learning. And I think it's already happening in like fields like program synthesis, etc. Yeah, so this intro slide is basically that we should be exploring these combinations of learning and reasoning and deduction. And I think both sides of this equation are important. You cannot just do learning, like for example, today with the kind of LLM revolution, or even before that, people were speaking about grounding the LLMs in some world knowledge, right? But like in my opinion, logic is the revolution that happened 100 years ago. That is kind of the most general way of giving us some world models, right? Like how do you express, I don't know, physics theories or mathematical theories? Like thanks to the work that these people like Russell or even Leibniz did for us, we have a very general way how to play these games with some environment. Like we don't just play some chess or Go, some kind of boring games, but we really can play the full mathematical game, right? And that includes physics and all of that. And I think these people like Popper are actually talking about it when they are speaking about how science develops. Like we build some kind of world knowledge, some theories, and then we try to break them by pushing them to their limits, like this, all sorts of stuff. Yeah. So the thing where I could do these experiments already like 30 years ago are these corpora of formal mathematics, which again was already pretty, it's a field that started like some 60 years ago. But already something like 30 years ago, you got quite big formalizations on which you could try to train some combinations of deductive and inductive methods and see how far it will take you. So that's kind of the intro. There is a bunch of slides, quotes that I have collected over the years. So Poincaré is one of the oldest guys who says that mathematicians don't just do proving, but they also use induction, guessing, etc. Obviously, there is Popper saying that the hypotheses are nets only you casts will catch. That there is Polya who says
no
that
parallel processing, that sucks.
That says certainly let us learn proving, but also let us learn guessing. And then the last quote.
Fora da Corina são todas super antigas. It will likely cause problems.
So there is this quote from
yeah, pois.
Oh, let's try. So there is this quote by Hemming, which is Galileo once says mathematics is the language of science, hence facing the same laws of the physical world, alien mathematics must have a good deal of similarity to ours. So I'll plug to it a bit later, but what I like about this quote is that some of the feedback loops that we have been trying and running between, let's say, learning and deduction, or some other search methods, have already shown us that the systems can lead to non-human solutions, that they can kind of produce this alien mathematics. So I think it may be also a bit relevant in this era of the LLM, where people think like the LLMs will just learn everything which is out of the internet produced by humans. But I think what we are doing is much more interesting in the sense that we really, these feedback loops can show us a lot of like inhuman design spaces, like we can really discover things which the humans didn't discover. Like you already had it in Go, for example, right? Like the AlphaGo Zero discovered some moves that the professionals considered to be wrong, but like the AlphaZero convinced them that they are not wrong. Yeah, I have a bunch of funny pictures stolen from Logicomics. So just to show you the typical tension between the deductive and the sort of more, I don't know, learning inductive camp. This goes back to Poincaré versus Hilbert, where kind of Poincaré argued that basically logic and formalism will kill mathematical induction, intuition. Then this is the other side, right? Like again from Logicomics, where Russell sort of quotes the Leibniz dream as dream to basically solve all our problems, not just mathematical ones, but all of it, like physics, law, economics, etc., by basically reduction to logic and computation. And this is Stefan Schulz. So we started a conference called AI and theorem proving like 10 years ago, and Stefan Schulz is one of the people who was doing machine learning and theorem proving even before me. His PhD thesis is in equipping one of the best automated theorem provers called eProver with machine learning methods. And he gave this funny talk at the first AITP called Deduction and Induction, a match made in heaven or a deal with the devil. So yeah. I don't want to speak too much too abstractly, so I put two quick demos. I don't know how quick they will be, and yeah. So the first quick intro or demo is this proving learning feedback loop that we do on a reasonably big formal mathematical corpus of something like 60,000 problems. And we kind of got it working relatively recently in 2019, where we sort of zoomed in on machine learning methods that are both efficient, like they are not very slow, and also quite powerful, that can be plugged into the state-of-the-art automated theorem provers. So the thing with the state-of-the-art automated theorem provers is that these are really fast symbolic solvers with a lot of very good heuristics. For example, I think until today, basically nobody has beaten the heuristics in such solvers in the propositional logic solvers with some deep learning, because that would make it really slow, right? Like so the let's say first order or high order automated theorem provers are not as crazy efficient as such solvers, but they are still like very, very efficient symbolic solvers. And guiding them with something like ChatGPT would be kind of silly, because like if you ask, let's say this symbolic solver does, I don't know, 10,100 steps per second. And if you wanted to guide each of these steps by some large language model, then you would be in big trouble, because it would really slow it down a lot. So you need to be a bit more efficient, or quite a bit more efficient with the machine learning guidance, but like such methods do exist. In this case, we took something called gradient boosted decision trees, which are ensembles of decision trees. And we took the unmodified automated theorem prover, ran it on this 60,000 problems from the Mizar mathematical library. And initially, with the unmodified eProver, we solved 15,000 of these problems. Then we trained these efficient gradient boosted decision trees on these 15,000 problems, and plugged them in a reasonably efficient way to guide the kind of search done by the automated theorem prover, and ran it again. We ran it in a kind of honest way. So the automated theorem prover without the guidance gets 10 seconds on a single CPU. And the automated theorem prover with the guidance is run also on a CPU, gets also 10 seconds of a CPU time. And with the guidance, like in the first iteration with the guidance, we do it in two different ways, but that's not so important. The better method jumps to something like 20,000 solved problems, thanks to learning from these 15,000 problems. So then you can train again. That's kind of the iteration, the feedback loop thing, and plug now the kind of more informed and smarter machine learning model again into this eProver, and try to solve these problems again in 10 seconds. And you get to something like 23,000. If you iterate this, I don't know, 6 times in this first experiment, then it takes you to something like 25,000 problems, which is something like a 70% improvement. So this is like one of the kind of prototypical examples of these feedback loops between the proving, the deduction, the search, and the learning, which kind of can guide the search and the deduction. We pushed it further when it started to work, and then put also graph neural networks into it later, getting us to something like 75% of the MISAR library eventually in 2021, but with higher time limits. So we can get proofs like this. This is in 4 minutes. You are not supposed to read it, just to impress you with the bigness of the graph. So this is like 360 step. And this is how that graph looks when it's the proof written by the human in the library. Again, you are not supposed to read it. This is my victorious announcement from 2021, when I called it the rise of the computronium at the time. This was before LLMs, before the ChatGPT thing. So what was kind of interesting is that for a lot of these problems in the MISAR library, you not only need some kind of typical mathematical reasoning steps, like some kind of natural deduction stuff, etc., but also quite a lot of algorithmic stuff, like I don't know, matrix multiplication, or like integration and differentiation, various normalizations, etc. And it looked like basically in this, you could call it Turing complete theorem proving framework, you can basically get the feedback loop to learn a lot of these, not just reasoning, but also pretty focused algorithmic tasks. So like one answer to the question of what kind of AI we need for doing math is that like you can imagine this as some kind of alternative to this today's world of LLM will do it all, is that you have some huge formal knowledge, like huge formal data set, and you have these kind of not so huge, in this case, this was graph neural network or gradient boosted decision trees, which basically tells you how to combine these pieces of the formal knowledge, which, by the way, include the algorithmic knowledge, right? So it can really do these things. This is the second kind of intro demo example. So it's an experiment that we have been running for 2 or 3 years now on the online encyclopedia of integer sequences. And it's not strictly theorem proving, but it has this kind of search, verification, and learning aspects to it. So this graphs shows you like the iterations of this feedback loop between the search, checking, and learning. So we are now, well, this was in the summer of 24, on roughly 700 iterations of this feedback loop. And on the y-axis, you get the number of the solved sequences. So in OEIS, the version which we are running has something like 350,000 integer sequences in it. And you can see that by the iteration 700, we have solved roughly 1/3 of it, like about 120,000. So the feedback loop looks roughly like this. So we have a very small Turing complete domain specific language for the programs that we are synthesizing. So you can see 2 examples here. One is 2 to the power of x, which is this loop 2 times x, x1, and we have x factorial, which is loop y times x, x1. So it's a very short program in this domain-specific language. And we are initially randomly, or you could say also exhaustively, that doesn't matter, generating programs of this shape. And the random or brute force enumeration takes you to, I don't know, depending on your resources, 2 or 3, maybe sometimes 5,000 of solved OEI sequences, like the very simple ones like constants, identity, and some linear functions, etc. And from those solutions, we learn. So after we verify them, after we check that the generated program is really generating a particular sequence, we create training data for a machine learner. We have tried different ones. The one that we have been running for longest time is a very small language model, which actually isn't even a transformer. It's an LSTM with attention, which we can train pretty quickly and also infer with it really quickly. And once we have trained this smallish language model, we use it for better informed generation. So we train it on the examples which say this integer sequence is explained by this code. And now, once we have trained it, we take all the sequences, the 350,000 sequences in the OEIS, we give them as an input to the language model, and we ask it for many suggestions, like 240 suggestions of the programs that could be explaining this sequence. So we get millions of explanations, and we very efficiently verify them. Like we try to see whether they do explain some of the OEI sequences or not. And if they do, we train on them again. So that again gives us this kind of search, verification, and learning feedback loop. And this is kind of surprising compared to the feedback loop that I was showing here, where like this theorem proving feedback loops are typically plateauing pretty early. Like here, after the 6 iterations, it already is doing quite a bit less than, let's say, in the first iteration. Here, it's really not plateauing for a very long time. And I'm kind of still thinking why it is. One conjecture why it could be like this is that it's doing basically 2 kinds of learning here. It's kind of doing symbolic inventions, like for example, when it invents the program for primes, it suddenly gets a huge boost, like I don't know where it was. Yeah, you can see these boosts after it invents various stuff. And for example, the program for primes is really important for explaining many other sequences in the online encyclopedia of integer sequences. So my conjecture is that this feedback loop hasn't really plateaued for these 700 iterations, because it has this combination of making like some symbolic breakthroughs or inventions and sort of statistically propagating them by the trained language model, which kind of, once it learns something, it sort of proposes it as explanation for other sequences. And if it gets confirmed, it gets a boost and it gets propagated further. The one interesting thing about this is that this experiment has been extremely cheap. Like this cost us like by now maybe $3,000 on the electricity, because we really train like very small language models. And also it has this alien aspect. So for example, for primes, we now have more than 50 different explanations. Some of them are not primes, some of them are pseudo primes. And some of them you really need to think quite hard whether they really are primes or pseudo primes. So sometimes we really need to ask mathematicians whether is this legal. Here is kind of a bit of a bragging slide what you can do with this language. So you can do expansion of square root of 8 in base 3. You can do sum of Statter convey $10,000 sequence. There is one program, short one for primes that I'm showing here. Some elliptic curve, Wolfram's 30,000 rule, 30 automaton. And very recently, we got the cube root of 2, and I sent it to Tom Hales, and he blogged about it, so you can look it up. And these are kind of the interesting jumps that you get when it invents something. Like, for example, when it when it invented primes, it made the jump. When it invented square roots, it made another jump, etc., etc. So this is really one of the funniest feedback loops that I have been running in my life. Oh, here is one more. So I have talked to a mathematician last year, Sander Daman, who is doing research in elliptic curves. And he told me to look at these 6 elliptic curves. So I looked it up. And we can solve the 3 easiest ones that he proposed to me, and we cannot solve the other 3 that he gave me. And again, we none of us, again, it has this alien aspect that neither he nor us understand how this code works. Yeah. Oh, okay. So these were the 2 quick intro demos to kind of let you know what I'm talking about. I have a slide about the history, etc. So there is this already things going back like Poincaré, Hilbert, Russell, Leibniz, etc. A very important or interesting guy in the history of all of this is obviously Turing, who obviously invented computers, proved the undecidability of first order logic, but he also basically started AI, right? Like in his 1950s paper. And even funnier thing is that the last chapter of his 1950s paper on AI is called Learning Machines. So if you think that machine learning is something very new, then no, like it's been. And he even proposes playing chess as something that you could have some learning process there. As I said, automated theorem proving has been really one of the first AI fields, with people like, I don't know, Herbert Simon, Martin Davis, etc., doing their work in the 50s and 60s, and these were really some of the first AI systems. You get people like Pat Langley and Doug Lennart working, for example, on automated mathematicians or like symbolic learning of Kepler laws in the case of Pat Langley. Then in the 90s, there was a group that I already mentioned, like Stefan Schulz and Jörg Denzinger in Munich, who really started to think about combining machine learning with automated theorem proving. And it's also very interesting because some of the quote unquote celebrated deep learning architectures today, like tree neural networks, were invented by them when doing research about automated theorem proving, because you work a lot with tree structures when doing math, right? So that's been pretty influential. Like I said, my master thesis was to try to learn the symbolic programs and inductive logic programming. And I would say basically for some 25 years now, some of us have been playing in this field of taking some big math corpus and trying to do these combinations on it. There is, especially for the younger people, I have watched it because I've been exposed for such a long time on the kind of intersection of these communities, how the buzzwords are changing. So I don't know, 10 years ago, people stopped saying machine learning and started to say deep learning. Then 5 years ago, they stopped saying deep learning and started to say large language models, right? Maybe 2 years ago, they stopped saying large language models and started to say AGI, or it was like, so if you want to kind of get deeper into these distinctions, then there is a nice talk by Ben Gertzel, who is like the founder of the AGI conference that he gave some 6 years ago in Prague, and where he kind of explains the distinctions between all these things. I have a quick slide about the practical applications of this work. So there has been for some, I don't know, today, let's say 15 years, a pretty interesting progress in this kind of Leibniz dream thing, in this idea that we will really formally verify in logic a lot of the stuff, of the at least important stuff that we are doing. So one breakthrough was the formal proof of the Kepler conjecture done by Tom Hales, like that's been officially finished in 2014. And that there is a big story to it. I will not go into it. Another one was a formalization finished in 2012 of the Phi-Thomson theorem, which is like the first big step towards the classification of finite simple groups by the team of Georges Gontier. And there is much more of it. The kind of industrial part of it is that people have, for example, verified a C compiler, COMCERT, like the group of Xavier Leroy in France. And for example, a very interesting thing is that several years ago, somebody did some really pretty strong testing of various C compilers. And there is basically only one C compiler which didn't produce any bugs when you kind of do some fuzzing, etc. And that's exactly this COMCERT, this kind of verified C compiler. So that kind of shows you the power of formal verification. Like if you have proved that it works, then it works, like at least unless you break some of the assumptions, right? So I would say since people like Byron Cook joined Amazon and started to create the really industrial automated reasoning and formal verification group, applying formal verification, like people like John Harrison are, for example, verifying the cryptographic protocols working on your phone today. So in the recent years, this has really become pretty industrially important, also like the field of formal verification. And obviously, the stronger and stronger automated theorem proving tools we can create for these people, the faster this process, right? The faster the formal verification. And then there is this blue sky AI visions, which I don't know, we are probably more interested in, but I already spoke about them. I will probably not speak much about learning approaches. I just sort of gave here this one slide to sort of reiterate that machine learning isn't just statistical machine learning, isn't just deep neural networks, isn't just language models, etc. So some people even started to call everything but deep learning classical machine learning, but that's total nonsense because neural networks are one of the most classical machine learning approaches. So there are really many things that you can do if you want to learn. So some of them are, for example, symbolic algorithms that kind of learn a symbolic algorithm. And I guess that's some of the stuff that might be close to the people here. And yeah, there is a lot of it, and I have no chance of going into it. What is also interesting for, let's say, understanding math or doing some kind of machine learning for math is like thinking about how to characterize mathematical objects. And again, the answer of deep learning and the kind of breakthrough with deep learning is basically saying, we don't care, right? Like we will learn it end to end. We will have more and more layers and they will do it all. And it's interesting how well that works, right? Like how really what kind of interesting stuff you can do today with the language models, etc. On the other hand, like I guess most of you here are mathematicians or computer scientists, so you know that, for example, transformer has some clear computational limitations, right? So if you, I don't know, wanted to behave like a program, then you can easily construct a program which will not be learned by a transformer, right? So then you can think about I don't know, more semantic or more computational characterization of the mathematical objects that you will feed to your machine learners. And sometimes it's kind of necessary or much more productive than relying on some limited neural network to do something that is kind of impossible for it. So it's also like a very interesting topic. Here is an overview slide about how, like, what are the various scenarios, how we combine learning with theorem proving. So the oldest task, which is kind of easy and most tested today, is called premise selection. Is this kind of high level thing where you get a big library of mathematics, you get a new conjecture to prove. And now if you fed the full mathematical library, which has, I don't know, 100,000 or 1 million facts in it, to an automated theorem prover, then the automated theorem prover wouldn't do much because it has kind of an explosive combinatorial search, at least 20 years ago. So what you can do, how you can help the automated theorem prover a lot, is that you basically machine learn on the 100,000 proofs that you already have in the library, which tells you like what facts are kind of relevant for which conjectures, and that allows you to prune the kind of much smaller number of the relevant facts for your new conjecture to try to sort of attempt the theorem proving with. So that's very productive. I may show you some pictures later. It's also kind of very easy for people who want to try some more expensive machine learning. So for example, the first thing when I started to talk to the deep learning people like 10 years ago was this task, like this premise selection, because you can train a huge deep learning architecture. And when you get a problem, you run it just once. It can take you, I don't know, 1 second. And then you run the fast theorem prover. So you don't care that it took one second, right? So it's a good domain for the deep learning, LLM, etc. people. Then there is this much more ambitious task of like low-level guidance of the inference engines of the automated theorem provers, which is what I was showing you in the very beginning, like, for example, this Enigma system, where the ambition is basically, okay, like this machine is really doing a lot of modus ponences or resolutions or superpositions per second, and I want it to be smart, right? And then you cannot use something very expensive, but as you have seen, you can do it with sort of reasonable machine learning tools. Then there is this mid-level thing where it's today quite popular, where it's somewhere between the kind of low level and the high level. It's especially used in the tactical theorem provers like, I know, Kolk-Hall, Lean, etc., where you have bigger blocks called tactics programmed in these tactical theorem provers. And typically to do one longish proof, you would invoke like 20 or 10 to 100 of these tactical applications. And that means you can, again, use some more expensive architecture. So again, it's a good, reasonable territory for the more expensive thing. Then you can do these things like, for example, theory exploration, where somebody gives you a theory, and now you are somehow supposed to develop good lemmas, like to basically develop this theory. So that hasn't been done much yet, but people are getting to it. There are all these feedback loops. And there is also auto-formalization, which is this task that we proposed some more than 10 years ago now, where the ambition is to take something like a language model and try to train, translate, let's say, a whole article written in LaTeX into like a formal setting and see whether you can verify it with one of these formal mass systems. So again, like it's quite interesting for the people doing language models today. I will not go into these demos. I may mention a bit this hammers, which is like one of the biggest applications of some of the things we are doing today. So you have a formal proof assistant. It became popular in Isabelle, which is, for example, a popular proof assistant, and a system called Sledgehammer done by Larry Paulson and later Jasmin Blanchett. But basically today we have hammers for almost all of the formal proof assistants. And the thing it's doing is that it takes a problem written in the logic of the proof assistant, typically some high order logic or maybe type theory, etc. It translates it to some weaker logic like first order, for example. It runs a strong solver like automated theorem prover in first order logic like eProver. And if it solves the problem, then it tries to reconstruct the proof in the sort of stronger logic. And for that, you exactly need this task of premise selection, like to select the facts that will make it reasonably easy for the automated theorem prover. And today this works. So for example, if you run Isabelle, if you are sledgehammering in Isabelle, which is what the Isabelle people do quite a lot, basically you are issuing many queries to these automated theorem provers and to these premise selectors, which are recommending different facts according to their knowledge. So we have roughly 40 to 45 success on a lot of these libraries. This is from 2016. The data from 2021 is 60% of these are in this kind of hammering mode. The first feedback loop that I did almost 20 years ago is this Malaria, this machine learner for automated reasoning, which basically does this premise selection combined with the theorem proving in a feedback loop. So it's kind of similar to this Enigma feedback loop, but in a simpler setting when you are using just the premise selector. And here is sort of a recent incarnation of it, which my student did a couple of years ago, where it's showing how the quality of the machine learner influences the number of problems solved in these feedback loops. So the better machine learner, in this case, the gradient boosted decision trees, is achieving more results in the feedback loop than the old machine learner. And this is showing you another interesting thing that is going on. So even though this feedback loop is sort of plateauing, which I already mentioned in the beginning, what is not plateauing is the number of alternative proofs that we are getting here. So alternative proof is a proof from different premises in this case. And even though you are not solving new problems, you are still getting new proofs of them. And it's kind of an interesting task or problem for the machine learners, because you somehow need to decide what proofs you will be learning from. Like if you have 20 or 100 different proofs of the same problem, which proofs will you learn from? All of them, some of them, only one of them, etc. There is, I should be wrapping up, so let me start skipping things more. So you can do really a lot of stuff. So for example, one of the stuff that I mentioned is that you can use model-based evaluation of your facts in your library as features for the machine learners. So that's something, again, which you will not get with any neural network today, because the neural network doesn't do combinatorial tasks like model or counter model findings. So that pretty strongly improves the premise selection task. You can come up with like various semantic features. We get a lot of boost from learning in a name independent setting, when we basically forget about the names of the symbols and we just look at the structural, at the graphs of the formulas, which helps with the kind of analogizing task. I will skip this. This is like another simple AlphaZero style low-level guidance task, which we did first in a simplified setting. This is about the enigma, which I already showed you, and some additional facts about it. I will say again, like we are playing with very fast machine learning architectures. For example, my colleague Martin Suda is improving to today the best automated theorem improver called Empire by using very cheap tree neural networks, which basically only look at the graph of derivations for each clause. They totally ignore what the clause is about. And it's extremely fast. It's well integrated with how Empire works. And it's working pretty well. Let me skip the mid-level stuff. Yeah, so I wanted to show you just one of the earliest neural auto-formalization things that we did with Sean Wang and Cezary Kalishik. So the auto-formalization is that you take LaTeX and try to automatically translate it, in this case, to Mizar, to some formal proof-assistant format. And so just to kind of give you the feeling for it, this is how the data looks. So you get the LaTeX and you get the formal language. And this is how the language model performed it's like 6 years ago after various amount of training. So initially, when you didn't train it too much, if you give it as input some kind of LaTeX, it produces gibberish. But after like this, let's say 7,000 training steps, at the bottom, it actually produces a legal formal language Mizar input. So this was done on synthetic data. It kind of doesn't imply that we have solved auto-formalization, but it shows you that these language models are pretty interesting for doing these tasks like translating from informal to formal. I will skip conjecturing because I already mentioned quite a bit. I can say some caveats, comments, and dark sides, but maybe I will leave it to the questions. And this is the conference that we have been running for 10 years. It's called Artificial Intelligence and Theorem Proving. So if you're interested in more of this, please come to Oslo in September. That's it.
A few minutes for questions. Who has a question? Come on, questions.
You have a question on how mathematical data is represented in mind. Is this a psychological question?
I have no idea.
Huh?
I have no idea how we represent mathematical data in our brain.
For simplest case, if it's a set theory, a set relations, do you have some hypothesis or kind of?
So when some mathematicians taught me math when I was a student, they themselves were commenting on this, and they were saying, oh, for example, I have a very geometric picture of it, but there is that guy who has a very algebraic symbolic picture of it. So for example, this old professor was saying that there are very weird professors of mathematics who have a very different representation of the mathematical problem than he would have. So yeah, I don't know. We need some neural link to do some experiment on mathematicians, probably.
Thank you. Thank you.
Any more questions? Yeah.
Just prompted by this question. In fact, I'm a mathematician, but I was reading a neuroscience paper some time ago, and there was something about logical deduction being rooted in a temporal part of the brain, whereas arithmetic is in a visual part of the brain. So that seems to be fairly standard. And one question is, when you do this, well, symbolic representation of everything, everything is just the same. So there is no, it's not very human-like,
Mhm.
right? So maybe you don't want it to be human-like, you want it to be better than humans for certain tasks. But this makes you wonder, whereas alien mathematics would be at all like our mathematics if aliens are blind or something. So maybe they just develop totally different things. And so this is an open-ended remark.
I was at some point going to a forcing seminar, and the guys there seem to me like, even though set theory and this forcing multiverse was something very symbolic, it looked like they have really internalized it in some weird way. So I think something definitely happens to a mathematician who works in some domain which looks very symbolic to the outsiders, but they still must create some internal, I don't know, mental maps or yeah, that's all I can say.
If we just focus on the last 3 years since the GPT-3 came out, what were the breakthroughs in this area connected to the LLM revolution? Is there any that you'd like to mention?
So my impression is that people have been trying to use LLMs more and more for auto-formalization. And like we had a workshop last spring in Bonn, which was like about bridging informal and formal math. And when I was talking to these people who were kind of pushing ahead with the neural language models I think in the Isabelle setting, they were kind of acknowledging that it's not yet working spectacularly well. Like it looks like, I know if you have a kind of a boring homogeneous domain, like people are training it for this IMO, for this math Olympiad, which however seems to be pretty like some kind of high school limited math. And if you throw a lot of training data in these restricted domains, then it seems to be kind of working to some extent. But if you go to some kind of unlimited math, like the Isabelle full archive of formal proofs, then it still doesn't seem to be cutting it. But like, you know, the development is like you just had DeepSeek last week, right, or whatever. So I would say that's one direction where people are pushing. Another direction, which is also slightly controversial, is that people are pushing a lot with LLMs in this kind of mid-level guidance, in this guidance of lean, coq, whole, etc. But again, like you have to be cautious, because like my PhD student had recently a paper for coq where they showed that the speed is really important. So they compared a very simple but fast machine learning method, like indexed k nearest neighbor, with the transformer, with a reasonably trained transformer. And they showed that the k nearest neighbor, which was reasonably implemented and indexed, because it does search so much faster, actually ultimately outperforms the guidance by the large language models, if you kind of do the fair comparison of it. So I would say people are trying. And another obvious direction is conjecturing, right? Like if you like the first experiment I was showing, it's a very small language model. I skipped the kind of GPT style conjecturing, which I was doing long ago. But like you can, I know I was just running DeepSeek last week when it appeared, and it seems to be doing pretty well. I gave it a task which could be quite hard for it, and it almost got it, but it took it like 10 minutes on the, so again, like the inference time is kind of incomparable with the systems we are running. But I think for these things, like some kind of high level conjecturing, it could be pretty interesting to try because yeah, well, at least that's my impression. Yeah.